All right, so we're going to look at something that's pretty cool, I think, in the world of calculus. It's what's called the fundamental theorem of calculus. So this is this idea of what connects the area under curve with the derivative of a curve. Um, so yeah, we're looking at how the rate of change is related to the area under the curve. So it's probably the biggest idea in calculus. That's probably why it gets such a fancy name. Anyway, let's see if we can start breaking it down. First thing to say is we've now got a function that we're going to call f of t rather than f of x. And you'll see why that's the case in a moment. So actually along here we have the t-axis. Okay, the first thing we're going to do is we're going to create an area function. So what that means is we're going to create some function, and we're going to call that function g of x. So this blue area is a function that depends on x. Now, x is some point on the t-axis. So I've got some point here, x, and we're saying that this blue area is the area under that curve, and you can see why that might depend on x. As x gets larger, the area under the function f of t will get larger, or similarly, as x gets smaller, the area under the curve would get smaller. Okay, so that's the first idea. This g of x represents the area under the curve f of t at some point x. Okay, the next thing we're going to say is let's create some other area that is separated by distance dx. So we're going to call this distance dx. So if we create another area, this red area that goes all the way up to x plus dx, we've now got this entire red area. Hopefully you can agree with me, you would agree with me that the entire area of that could be represented by g of x plus dx. So that's that entire red area. Because rather than going to x like we did with the blue part, we're just now going to x plus dx. And remember, g represents the area under the graph. Okay, so the next thing we might want to think about is what is this area of this section here? So just this part here. Well, hopefully you would agree the entire red area is g of x plus dx, and the blue area is just g of x. So you hopefully would agree that if we took g of x plus dx minus g of x, that would give us this area here. Now, a really core idea in this whole thing is we have to now relate that to the original function. And let's think about what this point here is. This point here is x, and it has a height of f of x. Okay. So what we can say is if we take this section and we made it really small, then the height of that rectangle would be f of x, and the width would be dx. So essentially what we're saying is this is a rectangle, more or less. If we make it really small, it's definitely a rectangle, and it's got a height of f of x, and it's got a width of dx. Okay, so this is our first key point here. What we can do now is we can actually divide everything by dx. So what we're going to do is we're going to divide both sides by dx. So divide it by the width of the rectangle. And that's going to give us this. It's going to give g of x plus dx minus g of x all over dx. And that equals f of x just by that rearrangement there. Okay, this might look a little bit familiar. If we are to take the limit as dx goes to 0 of this left-hand side, and what that means is dx is getting really small. So we're making these rectangles really small. So dx is getting smaller and smaller. Then we get the limit as dx approaches 0 of g of x plus dx minus g of x all over dx. And so what we can say is this hopefully looks familiar from first principles. So as dx gets really small, this becomes the derivative of g of x. And what you'll notice is the derivative of g of x is equal to the function f of x. So I suppose our final conclusion would be this. The area function, if we take the derivative of that, it gives us our original function. And by sort of the reverse logic, we could say that, all right, if the derivative of the area function is the original function, then the antiderivative of the original function is the area function. And so that's kind of the big idea here of the fundamental theorem of calculus. It relates the area function to its original function. So the derivative of the area function is the original function. And then therefore we could say that the antiderivative of the original function must give us the area underneath the curve. So hopefully you can see how that logic sort of combines to give us, yeah, the fundamental theorem of calculus.